purpose of this lab was to compare two samples of heat-treated 1045 steel. One was normalized through annealing process, which is heat above the recrystallization temperature of 900 degrees Celsius, and then brought back to normal temperature through the cooling through air temperature, room temperature, which is a slow process. And the other sample was quenched, which is heating to above recrystallization temperature, and then brought down to room temperature very quickly by placing in oil, water, in this case oil, which hardened the surface. The mechanical properties were then tested through Rockwell hardness test, UTS tensile testing, and then viewed its microstructure underneath the microscope.
The main idea behind this lab was the concept of annealing. Annealing is a heat treatment process where in our case a metal is heated above its recrystallization temperature and cooled in a certain manner to achieve different properties. To test this theory, we have organized two samples, one quenched and one that we will anneal and cool slowly. From previous lab, we hypothesize and the annealed sample will reduce the stresses within its grain structure and will thereby yield a high ductility. The quenched sample will be more brittle as its grain structure has more stress due to fast cooling.
Since steel is a softer metal, for its hardness we use the round anvil. The specimen being demonstrated is the quenched sample. We then turned the capstan wheel to elevate the sample. We positioned it to allow us to take the reading on the edge of the sample. We applied the minor load and zeroed the reading. We then applied the major load and waited for the needle to rest until we removed it. We recorded the reading and repeated the process for the annealed sample. We used the C scale to record our results, and the results that we achieved were 62.5 C for the quenched sample and 33.0 for the annealed sample.
First we zeroed the vernier caliper, and then we took the measurement of the diameter in 3 different spots to get the average. We measured it in inches. And then we measured the length of the samples, and we used the data for the UTS tester.
The data from the measurement section was then entered into the UTS tensile tester, which included the average diameter and overall length. These pieces then were, after this were entered, it was time to place the sample in the machine. First, you took the sample, placed it in the bottom half of the cylinder. Then place the second half of the cylinder over top, and then take an O-ring and rubber seal around it up through the bottom. Then place it in the top of the half of the machine. After this, a secure pin was put through to hold the pieces up there together. The second O-ring was placed on the bottom, and 2 halves of the cylinders were placed again there to hold together the bottom half of the sample. Another secure pin was used to hold this all together. After this, the machine was stretched to relieve any extra space in the machine, extra space in the sample. The machine was then zeroed, including extension and force. It has now been time to begin testing. The bottom half stood still as the top experienced greater and greater force until the sample will break. After this, the broken pieces of sample were taken to the cutter and preparation for next part procedure.
The sample broken from the UTS tester was taken to the cutter for cutting because we need the shiny smooth surface later. So the broken part is placed in the cutter very carefully. The part is then tightened. Then we place the cover over the cutter because sharp cutting pieces can flew out. Coolant is also used while cutting in order to cool down the heat generated by a cutter. We can see while cutting that spark are produced. Water acts as both lubricant and coolant. We need to cut the part slowly in order to prevent uneven cutting edges or to prevent breaking of the blade. Cutting the part to make sure that cutting wheel is completely stopped. Then we take out the sample and use it for our further process, which is heating the material with bakelite powder. If our cutting is very accurately, then we do for our further process.
Each sample was put in the bakelite machine to turn the small cut samples into a puck. This process took 10 minutes to cure and 10 minutes to cool per sample. The purpose of the puck was to allow for easier handling and identifying of the sample.
After making the part, we grinding the part on 3 pieces of paper, rough, smooth and smoother. And we slide the part in each papers like in rapid motion and spend nearly about 2 to 3 minutes in each paper and grinding the part very well. And it's very helpful if we grind the part very well because it show a very clean face on that part. And then we going to the polishing material. This process clean the material very well. While polishing, we put some polishing powder and distilled water, and we polish the material to get rid of all scratches. When all scratches removed, then clean the material with distilled water and dry it with clean paper.
For the etching process, we use a dropper to extract 2% nitrile solution and then mix it around the dish. And afterwards, when we have taken the sample, we take the metal and move around the dish for about 45 seconds. And afterwards, when 45 seconds are over, we rinse it with distilled water to stop the etching process. We take a napkin to clean it off. This process will show us the microstructure under the microscope in a very clear manner. Etching uses microfabrication to chemically remove layers from the surface of the wafer. It is a critical important process, and every wafer undergoes many etching steps before it is complete.
Here we're looking at the microstructure of the sample after it has gone through the etching process. This picture shows what the oil quench steel microstructure looks like. We're seeing the grain sizes, the amount of carbon in each sample, with the quench sample having more carbon content, stating that it is a harder material. And also in it there's martensite and carbide. This picture shows the annealed steel microstructure having a larger grain size, less carbon content, more ferrite and perlite.
This lab consisted of taking 2 samples of 1045 steel, which were heat treated at 900 degrees Celsius, and placing them through several tests to compare the differences between hardness, strength, and microstructure. The reason that the steel was heated above 900 degrees Celsius was for the steel to surpass its recrystallization temperature. When the steel is above recrystallization temperature, it changes structure to the original state. If the metal was cold worked, it releases the stress in the grain structure. Also, the structure will change from base cubic center to face cubic center. When punched, the steel pieces can retain the face cubic centered structure. The difference between the samples was that one was annealed, which is the process of heating a sample up above its recrystallization temperature, and it is allowed to cool to room temperature very slowly. And the other sample was quenched, and this is the process of rapid cooling in oil. Quenching causes a sample to become harder, however, it also becomes brittle. Annealing also produces a stronger metal than cold work steel. However, it did not produce a nice surface finish.
The first test that was conducted on the steel samples was the hardness test. This test determined that the oil quench sample was the hardest. The annealed sample was only about half the hardness of the quench sample. These results are valid as oil quenching is supposed to make the sample harder. The annealed sample was predicted to be the softer sample due to the fact that after normalizing the structure, it will return to BCC, which is a more malleable structure. The second test was the UTS tensile test, which showed the strength and ductility. The annealed sample was more ductile and was stronger. It stretched more and had a higher breaking strength. Third and final test was viewing the samples under a microscope. The samples were cut, polished, and etched. It was then viewed under the microscope to examine the microstructure. The annealed sample had more defined outline of boundaries with the carbon, while the oil quench sample was more mixed as the carbon seemed to be mixed more thoroughly within the sample.
Annealing steel helps to remove the internal stress which occurs when the steel is cold worked. This process is used for steel about to be welded to help prevent cracking when welding two pieces of steel or other metals. Oil quenching is good for hardening a metal and making it more durable and easier to dimension. After all the tests, the results showed that the heat treatment had made the steel softer and more malleable if the sample was allowed to normalize. When quenched, the sample becomes harder but more brittle. The microstructure also shows the presence of more carbon in the quenched sample, unlike annealed sample.
So we can conclude from the result that quenching and annealing both have very different effects on the mechanical properties of steel. The oil quenched steel was harder but more brittle, while annealed steel was softer but was more
Can be
ductile.
used to make steel easier to shape and manipulate as well as to prepare the steel for cold working. Annealing is a process in which we heat the material in furnace. After soaking time, we cool down the material at very slow speed. With annealing, the material is soft and easy for shaping. Quenching is also used for the materials. Quenching is used when a high level of hardness is required, for example like tools, as they would be used rapidly in our everyday life. Quenching is a process in which we heat the material above recrystallization temperature. After that, we dip the material in oil or water, and it is also called oil quenched and water quenched. It is very important to know the ways quenching, annealing and other processes impact the properties of different materials, so it is possible to achieve the most effective and efficient product for our daily life or our engineering practices. Thank you.